Good morning and welcome to our next YouTube session for National Science Week 2020 here at the Queen Victoria Museum and Art Gallery in Launceston, Tasmania. This morning I have with me David Maynard, who is our Senior Curator of Natural Sciences here at QVMag, and we also have Dr Beth Fulton coming in on Skype from Hobart. Dr Fulton is Research Scientist with the CSIRO Oceans and Atmosphere, Research Program Leader, Environment and Ecosystems at the Blue Economy Cooperative Research Centre. So Beth has a number of hats and will be speaking to us a bit later on about the blue economy. Today we'll be speaking about water on Earth and elsewhere, the importance of water to life on Earth, and a bit later about the blue economy with Dr. Fulton. Do remember that you can ask questions online, and around about 10:30 we'll be endeavouring to answer as many of your questions as possible. So we'll start off by talking a bit about water on the Earth and other places we find water in the solar system. And I'd like to show you a few pictures now of some of the places where we find water. Here we are looking at a very famous picture of our planet Earth, and it was taken by the Apollo 17 astronauts on their way to the moon in 1972. And we can see here so much blue. We often call the Earth a blue marble, and in fact that's what this picture's been called. And that is where we have the oceans. The Earth is about 70% covered with water. So this is one of my favorite pictures actually from all of the Apollo missions, and it's not even a picture of the moon. But we found that there is actually water on the moon. Before the Apollo missions went up, and even for some time afterward, we didn't really know about the fact that there was some water on the moon. But in the 1990s, the Lunar Prospector spacecraft discovered some evidence that there was water near the lunar poles. And a lot of the research that's been done since has shown that there is water in the form of ice deep in craters in the lunar polar regions, especially near the moon's south pole. How did it get there? One idea is that it may have been transported there by comet collisions on the moon, and the water was, once it settled inside those craters where sunlight never reaches, it remained as ice pretty well right throughout. And that was indeed an early idea about the way water arrived on Earth, from impact from icy comets. A bit later on, the favoured theory was that asteroids brought water to the Earth because there's a lot of hydrogen and oxygen in asteroids. And indeed, that is the leading theory even today. But some more modern research has shown that some of the water on Earth might have been primordial water, water that was basically present in the solar system in the form of hydrogen and oxygen and got incorporated into the Earth as it was forming. Quite frankly, the jury is still out on a lot of those matters. Mars is another place where we find water, and this is a famous picture of Mars taken by the Hubble Space Telescope. Here we can see one of the poles of Mars tipped toward the Earth by some 20 degrees or so. We can see one of the polar caps. We do know that water is incorporated into the polar caps, especially into one of them, although there is also a lot of carbon dioxide there. We found that there is very strong evidence that there was once water flowing on the surface of Mars. Here we can see some very early pictures to show places where water may indeed have been flowing. Later missions have shown that on Mars there are many places where we have evidence that liquid water flowed. Here we can even see an image of Mercury showing places where water seems to have been discovered in the polar regions of the craters of Mercury, just like on the moon. And one of the more significant discoveries in modern times over the past few decades is that Jupiter's icy moon Europa seems to have an icy ocean underneath the surface. This is a very significant thing to think about because, as we'll talk about in a moment with David, water and life are so strongly linked together, and there is even the possibility that there may be some form of life underneath the surface of Europa. Indeed, there are some missions planned to go to Europa. One particularly ambitious one is to drill through the ice and send a craft underneath to go down and see what's there. This is at the forefront of our technology, of course, but there are certainly missions planned to go to that moon. Moving out as far as Saturn, we also know that Saturn's rings contain a great deal of water. They're a mixture of rock and ice, but there's certainly a lot of water there, and in Saturn's moons as well, particularly the moon Enceladus, where we can see that there are geysers sort of shooting out from the surface of Enceladus. And a lot of these observations have been made by spacecraft that have been going out through the solar system over the last many years. So that's a bit of a rundown of water on the Earth and other places. We also find that there is water in other places in the universe as well, by deducing the mass and density of planets that we're finding in orbit around other stars. It's possible to deduce that some of them may be composed of quite a lot of water. So water's certainly quite common in the solar system and our galaxy, and no doubt in the universe as well. But let's get back to the Earth, because David is here to speak to us this morning about the importance of water to life on Earth. So I'm going to hand over to David now to tell us a bit about that.
Thanks, Martin. How to sum up the importance of water to life on Earth in a few minutes? That's a bit of a tricky one. So I have had to prepare a few cheat notes to make sure that I am as succinct as possible. It's pretty obvious that water is vital to life. Without water, we simply could not have life. And you've already said that most of the surface of the planet is covered in water, 70%. So perhaps we should be calling it planet water or planet oceans, not planet Earth. 96% of the water that is on the planet is in the oceans. Those oceans are just so important to us. They produce over half the oxygen for life to use. It's got around 50% more holding capacity of, it's got 50% more holding capacity of carbon dioxide than the atmosphere. And 90% of the water that is evaporated and feeds into the planet's water cycle comes from those oceans. So where's our rain come from? From the oceans and the evaporation there. Also, the water acts as a bit of a thermal blanket, an insulator for us. Currents take warm water away from the equatorial regions down towards the poles, and so that works to help temper or moderate the temperature extremes. Without the water, we might have temperatures more similar to Mars. And Martin, what would be extremes of temperatures on Mars?
Oh, well, really, an extreme temperature on Mars on a really warm summer's day at the equator, David, would be about plus 20 Celsius, which actually sounds pretty good. Oh. But at night, it goes down to about minus 70 or minus 80 pretty quickly too after the sun goes down. And in the polar regions, it's typically around minus 125 in the winter. So it can get pretty cold pretty quickly.
So there you go. So having water really helps to balance out those temperature extremes. The oceans are very biologically diverse, from the smallest plankton to the blue whale, and most of the biomass of planet Earth lives within the oceans. In fact, a lot of it would live within the top 200 metres, even though the oceans are as much as 11,000 metres deep. And the role of plankton in the oceans and is undervalued. It is the start point for so much of the globe's food web. So it's very important, and I'll be talking more about that on Tuesday with Dr. Chris Maiden.
Yes.
The oceans are obviously important to humans as well. You've only got to look at where most people live. 40% of the population lives beside the water. So there you go. It provides us with some benefits, which we'll have a quick look at now. If you could flash my image up there. Mm-hmm. This is from America, so it's only considering their direct benefits, but it has the same things we're talking about in that it produces a lot of oxygen. It provides us, one I haven't talked about is just the value of transportation. We would be isolated as a continent if we weren't able to use those oceans to transport all of our goods around. There's also economic benefits, whether it be through, for instance, fisheries, and also we use it for recreational purposes. We also benefit from the oceans in terms of seafood. And one that we don't think about much is medicines. There could be the cure for cancer in some of our unknown sponges. And I'll just make a point with food. The role of marine plants in food is under realised in the community. Every day we all ingest a bit of seaweed. There you go.
Wow.
Yeah. So it's the oceans provide us with a lot of unknown benefits in respects to
Right.
So the other thing I just wanted to mention was, you could probably remove that. Thanks, Martin. Fresh water is really important, obviously, but there's only 2.5% of our water is fresh water. So it's a finite resource. We have to do better at caring for that water. Less pollution and use it more wisely. So be water wise in everything we do. Now, Martin, you were going to ask me a question about how life started on Earth.
Well, yes, indeed. What are your thoughts there, David?
Well, funny you should ask. There's a number of theories on how it started. Probably the most realistic one at this moment is the role of hydrothermal vents in the deep ocean. Hydrothermal vents are like jets of superheated mineral-rich water that are shooting up out of the seabed. And around those vents are these amazing communities of the most bizarre, most wonderful creatures. And it's thought that organic compounds may have first formed what we think of as a protocell. Protocell is just literally that, a combination of organic compounds. The latest research, they've tried to replicate that in the lab, and they've been able to form those protocells. They haven't been able to get a cellular wall. So why do they think it could be that thermal vents? They used water that was very similar to the ocean. They used water at 70 degrees Celsius, and they used water that was very, very alkaline. That's probably the outlier. But from that mix in a lab, it looks like they can better support the theory of hydrothermal vents being the starting point of life.
Fantastic, yeah. So those hydrothermal vents you mentioned get to about 70 degrees, but they can get much hotter,
yes,
can't they?
Yes, I mean, they're in the deep ocean, high pressures, so there would be high temperatures as well. But in the lab, 70 degrees seem to be the sweet point.
But is there a temperature in the real hydrothermal vents beyond which life simply couldn't survive?
Yes, the hydrothermal vent itself, it's super heated, and so the life lives beyond that, within the range that suits life, but they're not at the very point of ejection.
Right. Yes.
There you go.
Fascinating.
So there you go. The oceans, the water, critical to life on Earth.
They are indeed, and in fact, as we search for life in the universe, and in fact, primarily in our solar system, the search for life and the search for water are so strongly linked together, and David certainly linked them together very, very well for us today.
And I'll link back to yours earlier, Martin. The icy moons of Jupiter and Saturn, as you said, they could hold those sort of hydrothermal vents that could support life.
Indeed.
Beginning of.
Indeed, and that would be fascinating to learn a lot more about, and hopefully it won't be too long before we've got a lot more information about that kind of thing, and certainly that that search for water is very, very important. Mars is our key one at the moment, of course, with so many spacecraft going to Mars, rovers on the surface of Mars, studying the surface, and as I think I mentioned earlier on, the study of minerals that could be or would have been formed in the presence of flowing water that isn't there today on Mars, because the conditions on Mars, the atmospheric pressures and temperatures don't allow liquid water to be stable. But long ago, we think it was. We're pretty sure it was. And one of the big questions about Mars actually is why Mars has changed so much. And I guess that helps us to learn a lot more about other planets as well and how they can change, and maybe even the future of our own Earth. So yeah, some great things to think about there. What I'd like to do now is hand over to Dr Beth Fulton, who has been patiently waiting while we've been chatting about all sorts of things. Beth, once again, good morning, and I'd like to hand over to you now to speak a bit about the blue economy.
G'day, thank you for having me. I'll just get rid of that. So it's great to be here this morning to talk to you about the blue economy, which is a really important part of Australia's economy. As you heard just before, fisheries and aquaculture and things like that are central to Australia's blue economy. We have the third largest exclusive economic zone in the world. That's the space of water around Australia where we get to say what happens, so to speak. And that already produces $40 billion a year and is likely to double in the next 10 years. So it's a really important part of the way that we do things in Australia.
Indeed. And we have some images here, Beth, that you've provided for us. So maybe we can get those up on our screen now, and you can speak a bit about what these are. And we're currently looking at a wonderful array of platforms in the ocean here. So perhaps you could describe this one to us. I love this picture. It's great.
So this picture comes from a partner in the blue economy, CRC. They're an engineering partner, DVNGL. I hope I got their name right. Apologies if I didn't, guys. Basically, the idea is that in the future, we're going to be using more and more of the ocean. And how do we do that sustainably? So if you can imagine everything we do on land, that's now moving into the ocean. And one way of doing that is to have big floating platforms that you link together a bit like Lego sets. So you have different things happening on different bits. You can see pools on there, and in those pools you might have aquaculture pens for fish or algae or kelp, like we heard before, that we all take in every day. There could be oysters. There's lots of different things that you might have in there to both produce food but also clean up around the place as well, have a really closed system that's really healthy, like in a natural ecosystem. There's other parts for energy generation. Australia has one of the biggest renewable energy potential in the marine sector. It could also be even accommodation and housing. Places like America even thinking of having them as big offshore ports run by robots, so both for security, but because the inshore coastal area is already pretty full. So if you move offshore, you've got a lot more space to do things.
So Beth, tell us a bit more about how these platforms are supported. Are they actually floating, or are there solid supports underneath? How is it all set up?
So there's lots of different ways the platforms can be made. So in the Northern Hemisphere, particularly in the North Sea, they've already spent a lot of time trying to put these platforms together. That sea is relatively shallow compared to the deep ocean. Those platforms can be moored or on pylons, so, connected to the bottom of the ocean, a bit like oil rigs are, and things can live around those. But you can also have floating ones. So some of those float right on the surface. China's already got one of the largest floating photovoltaics in the world. So that's a whole big set of solar panels floating on the top of the ocean. You can also have ones that submerge just below the ocean. In fact, some things require to be submerged so that they pump up and down. The kind of modular system you saw just before is most likely going to be floating. In fact, they have floating suburbs already created in the Netherlands, and indeed a dairy farm in Rotterdam Harbour. So anything could be potentially connected together in that way.
That's amazing. But what about the waves? Are they stable if they're floating? I mean, what sort of damage could be done with a storm or with all sorts of tidal effects and so on?
So you do have to be conscious of how energetic the ocean is. It might look placid on some days, but as people might have seen in the news about Sydney Harbour's ferries during the middle of COVID earlier, the waves can be quite enormous when a big storm comes in. And indeed, in the southern hemisphere, it's even bigger problem. So if you think about our planet, the northern hemisphere is the land part of the world, and the southern hemisphere is the ocean part of the world. So
Right.
even though people have started building things in the northern hemisphere in places like the North Sea and Alaska that we see on TV and think of these huge waves and these huge storms and the exciting movies, the Southern Ocean waves are a lot bigger and a lot stronger. So they're even pointier, which puts a lot of stress on things that float past. So things that are built for the Northern Hemisphere can potentially fall apart a lot quicker around Australia and the Southern Hemisphere. So it's about finding the right engineering. You can build it in a sensible way. You might build it so it acts like a ship and rides it through. You might build it so it sinks down under the waves, so it's not being buffeted. But they are some pretty big waves that we already face. So the aquaculture pens in one place west of Wedge in Tasmania, those pens are so robust and built to purpose because they already have to deal with 14-metre high waves. So you have to respect that energy right from the start.
14 metres is quite something, isn't it? Yeah. Beth, these are based on triangles here, I can see in our picture. So is there a particular reason for that? As we all know, triangles are great to use for stability and so on. So what's the story behind the shapes here?
So I'm going to defer that question because I'm not an engineer. I'm a mathematician and a marine biologist. It could be partly that it's an artist's impression, but it could be that, as you're right, triangles are fairly robust in terms of being modular. What you see in the oceans are often the very basic shapes of triangles, squares, circles, hexagons, and sometimes it comes down to the purpose. So if we think about some of the fish pens on the planet in a fish farm, there's some species that don't like corners. So a big tuna doesn't like to have a corner. It doesn't know what to do with a corner because those big tunas don't live in a world with corners. So you have to have round pens and globe-like pens for them to feel happy and at home.
Wow, that's fascinating. Yeah, and are there other kinds of fish that have similar problems with shapes and structures and so on?
Most animals will have some shapes that they're not familiar with. They just haven't had to deal with it. Even in square pens, you'll often find that if an animal's unwell, it'll go hide in the corner. So you can actually build some of that insight into how you design things so that it's easier to maintain, and you can funnel basically animal social distance. So we all heard about social distancing over the past of our past 6 months, but unwell animals socially distance. Lobsters, fish, things that live close together, if they're unwell, the healthy animals will either move away or the unwell animal typically takes itself away. So it's a concept that even the animal world's on top of.
That is fascinating, considering what we're going through at the moment, as you've said. Beth, are we going to get to a point where people will be able to see these sort of structures sort of out near their horizon, closer than their horizons? Or are the structures more likely to be well away from the land so that they're sort of out of sight?
That's a conversation that's ongoing around the world. In some locations, they are already within sight. So if you walk along the shores in Netherlands and Germany, you can see offshore wind platforms from the shore with boats weaving in between them and people on the beach. That's a choice that Europe was comfortable with because that's a very industrialised landscape. In other places, such as northeast United States, there's been quite a fierce discussion amongst the local community about whether they want to see it or not. In Australia, we're just starting that conversation, I think, and my suspicion is that it'll be more offshore. We would like to use our oceans and have access to our oceans. It's already a pretty crowded coastal space with 80% of Australians living within about 50 kilometres of the ocean and visiting fairly regularly. So my suspicion is that it's going to be further offshore, which gives us more space, but does mean that we have to do it in such a way that we don't create new issues when we move out into those depths.
Right. Let's move on to another picture that you'd like people to see here, Beth. And this is a rather fascinating looking one. We appear to have an underwater enclosure with lots of fish in it. Maybe you could talk us through this image.
So that's from a fish farm off Hawaii. So they've already been experimenting with how you have a fish farm in really, really deep water. So Hawaii is a very large mountain chain. So just the islands you see at the top, at the very tops of those mountains poking out, they're some of the largest mountains in the world. And so the sides are very, very steep. So you can get into very deep water quickly. So the Kampachi Farms, as they were called then, they've changed their name since, but they were one of the very first people to start doing this deep water farming. And one of the cage designs they've trialled is the underwater cage. So basically subsurface and robots can go in to look after the fish, duck down, and they get robotically fed, so remotely fed. The gentleman sits in his office in Hawaii and presses the button and they get fed offshore. He sees the live camera stream and they... not so much Kampachi necessarily, but around the world, people using those kind of designs are starting to use robots to do the net maintenance, little drones swimming around looking at the fish and cleaning the edges. I think the best anecdote I heard from him was it gets a little bit exciting when you have to put a diver into a pen like that, because you've got to swim really fast from the boat into the pen and avoid any predators that may be lurking around attracted by the fish.
Well, that sounds very interesting indeed, yes. So that's great. Let's move on to another one you've got here, which is a beautiful image. We're looking at fish around some pylons with a lot of life on the pylons.
So people often think of humans imposing themselves into the ocean. It's the last great wilderness, but the ocean imposes itself on humans really fast as well. So once you've put something in the ocean, within a week, it's got something trying to live on it. A lot of the older structures like wharf pylons and oil rigs have become home to very rich communities of animals. So it is a little bit of a tug of war of the heart when you get to the end of the life of an oil rig. You know, you want to clean up after yourself, but you have to do that with some thought, because in some locations, the very last of the corals or the very last of the seaweeds and stuff like that are living on the edges of those platforms because humans aren't allowed to go up and touch them and fish them and things like that. That's in very degraded locations. In Australia, we're not in that position. We have a very rich wildlife in our oceans, but it doesn't mean that we can't think about how to design these things from the start so that you don't have that tension, that you can build room for these animals to live right from the start. And the universities in Sydney collaborated with Volvo to do exactly that kind of thing for harbour walls, where they built little niches and nooks and crannies into the wall of the harbour so that animals could colonise right from the start. So it's living with nature so that you provide a home for the animals without undermining what you need it to do on the human side of things. So whether that's energy generation or creating a sea wall or being a platform for aquaculture, you can live together and make space, because the ocean's going to want to be part of that space anyway. So it's, you know, work with something rather than fight against it is usually a pretty good thing to do.
It's all about different forms of life on the earth learning to live together, isn't it, really?
Yep.
Indeed.
Can I make a comment?
David, yes.
So that's effectively an artificial reef, which is something that is actively worked on, as you're saying, to try and encourage biodiversity in areas that don't have, say, hard structures. But I really like hearing that there's the idea of trying to include a size range of homes, habitats, holes, because I've dived off Marion Bay doing lobster research in southern Tasmania, and you could find the very smallest lobsters, but there was a bottleneck of habitat missing, and so there wasn't the larger lobsters being able to grow in that location. They basically, larger lobsters had to come from external to use the habitat that did fit them. So incorporating those different design factors can really increase biodiversity. Great to hear.
Yeah, very good. And what about shipwrecks? Is the same situation? Does that occur with shipwrecks, where we've got this sort of life, basically big making use of shipwrecks. I mean, my first thoughts go to the Titanic, but there are loads of shipwrecks down there. So is this the same situation as you would find then in shipwrecks?
Yeah, so which is often why they're used to create the artificial reefs we just heard about. So sinking a ship infrastructure and letting life colonise it is some of the, has been used to create artificial reefs in a whole bunch of places because it becomes an exciting diving site. Some of the most famous dive sites around the world, with Yongala up on the Great Barrier Reef being one, is exciting because you get to see a piece of old infrastructure, but more importantly because of the enormous life that grows over it and colonises it. In some places where you're diving around of something that's been there for a very long time, you don't even realise it was a ship or an old statue. So in the Mediterranean, it's not just shipwrecks, it's submerged cities and things like that have been colonised by the animal life. And it's a little bit, it's a little bit disconcerting the first time you see a large shark swim through a statue of Venus or something like that, but it is quite amazing once you've actually seen it.
Oh, that would be quite fascinating, actually. And I know David's an avid diver, aren't you, David?
Yes.
And have you've been down to some wrecks?
Love a shipwreck.
Yeah, great, fantastic stuff. Yeah, it's now just after 10:30, and we will endeavour to answer some questions. We don't have all that many questions on the chat at the moment. We do have a comment that a cure for cancer from the sea would be magnificent, wouldn't it? So what was the thinking? You did mention that earlier on, David. Is there any detail that we have on that at the moment?
Well, I made reference to sponges, marine sponges.
That's right.
They're an animal. They're a very poorly known animal. The taxonomy and such, we continue to discover new species. So I know that a number of places, including Queensland Museum, have been trying to extract compounds from sponges to see whether they have any medicinal or other purpose. And the Australian Maritime College here in Launceston, probably going on a decade ago now, was hired to go out and harvest sponges from Bass Strait for that very purpose. So it's not only government agencies, but there is the private sector also looking at what compounds may be out there.
That's great, yes. And also going back to what you were saying earlier on, we all ingest a certain amount of seaweed all the time.
Yeah.
And I remember when I was a child being told that there was seaweed in my ice cream.
That's right.
And I was absolutely fascinated with that and couldn't work out how it got there. But how is it that there's seaweed in ice cream?
One of the extracts is carrageenan, which is like a gel, and it makes your ice cream creamier and it makes your toothpaste creamy.
Right.
So there you go.
Well,
it's in some peanut and soy products. So
fantastic. Right. Really interesting stuff. We've had a comment from somebody who is listening in from America right now in South Carolina. So we have an international audience this morning. I received a message earlier on that there are a couple of people who are watching from Thailand as well. So we really are very international today. We have another question. What will be the effect of ice melt due to climate change? What effect will that have on the world's oceans? David or Beth? Beth, would you like to comment on that?
So in the immediate area of the ice melt, it actually makes the water fresher and changes the currents and the weather conditions around those local areas, and that's already happening in the Antarctic and the Arctic Ocean. Globally, if it's sea ice, it doesn't make much of a difference to the ocean's depth because it's a bit like an ice cube melting in your glass of water. It was already there. But if it's ice that was on land, so it was Antarctic ice or Greenland ice, as that melts, it does flow in and it will increase sea level. So we're looking between, the lowest level I think I've heard is about 1 metre by the end of this century, but potentially many more metres. There's a lot of uncertainty about this because we're not quite sure how fast the ice is going to melt. So you've got just normal surface melting, but as that melts and slides under the glaciers, it acts as a lubricant and the whole thing can slide off much faster. A few times in the last decade, the whole surface, like a centimetre or two of the whole surface of Greenland has melted in the course of a couple of days. So that is now quite a significant concern. And while everybody's attention's kind of been on COVID for the last few months, through the last couple of months in the Arctic, it's had some of the lowest ice cover that it's ever had. So it is an ongoing issue that we are going to have to think about, particularly given 40 of the world's mega cities, the biggest cities on the planet, are right on the edge of the ocean and will go underwater likely by the next end of the next century or the next couple of centuries.
I might add to that too, of course, the loss of the ice caps does affect some of our wildlife. For instance, the old polar bears losing habitat very quickly, and its food as well. So it's not just about us humans; it's a whole system problem.
It's a pretty delicate balance, really, isn't it? I think, as we've been speaking about. We have another question. We hear a lot about plastic waste in the ocean. Now, actually, last year in Science Week here at QV Mag, we talked a lot about plastics and the problems that we're having with those. But has the blue economy, Beth, got a process to help that decrease? Is there some work being done on that?
So there's a few different things to focus on there. One is just reducing it in the whole of the economy, which is the circular part of the economy, but particularly when you're in the ocean, trying to minimise its impacts on the animal life that lives there, and including the materials that the blue economy uses. So if we think about things like the nets that are used in aquaculture pens, making sure that they're recycled and reused. So at the present moment, companies in Tasmania, for instance, take their old nets and recycle them into material that's used in road surfacing and pavement making and that kind of stuff. Elsewhere in the world, they're actually turned into skateboards, swimming costumes, and a whole bunch of other things. But ultimately, it's about also trying to find materials that get away from having to have that microplastic interaction. And that's where you can, again, look into the ocean for inspiration on building materials and parceling materials that do what we need it to do, but don't have that same kind of plastic overhead. As we heard before, 75% of all animals still live in the ocean, and they've got all that diversity, and life began in the ocean, so they've been evolving for a lot longer. There's a lot of solutions that are literally in ocean animals or inspired from ocean animals that'll help us crack that problem too.
Certainly is a problem too, isn't it? Well, a big increasing problem. We have a question about water being found on the moons and whether there are other factors that are absolutely necessary for simple aquatic life to exist that we don't find on those moons. That's a very interesting question. Certainly we'd like to know a lot more about what's in those oceans, the composition of those oceans. But David, we do know that the oceans underneath the surfaces of those moons are likely to be extremely salty. And also with Ceres, the asteroid as well, we found that there's some material that's come up to the surface through impacts that shows that there's a very salty ocean underneath. Would the saltiness of an ocean be conducive to life, or would it detract from the possibility of life?
It wouldn't stop life necessarily. I mean, here on our planet, we've got animals that live in supersaline type habitats. Think of when we were kids, which was only a few years ago, we used to be able to buy sea monkeys off the back of the comic book. Artemia is one of the life forms that live in supersaline type lakes here on planet Earth. Right. The other things that would be needed, we assume it would be a carbon-based life form, and then you'd probably need a bit of oxygen mixed in there as well. So,
yes, but we're making assumptions there, aren't we, too?
It could be a silicon-based life form.
Yeah, and also, of course, the temperatures as well. Yeah. The temperatures will be different, and so it seems to me that it's a matter of going there and checking it out, really, to find out a lot more about that. So so many variables there. Another question, what is the current thinking on the composition of comets? Do we still think of them as dirty snowballs? Well, in a sense, we Whipple going back to around sort of essentially what they look like. Many different elements, many different molecules. They're made up of a lot of water, carbon dioxide, carbon monoxide, magnesium, silicate grains, and so on. There's a lot of different substances in comets. But But the question was, does that mean there's a possibility of life catching a ride? Actually, there was a theory a long time ago that was called the panspermia theory, that life was actually brought to Earth by comets. Well, that's quite controversial, of course, but certainly comets are made up of very primitive material from the early stages of the solar system. That studying comets is extremely important to help water in the solar system and the history of the whole solar system. One thing we have learnt, though, from the observations of comet Churyumov a few years ago, is that the kind of water that's in that has what we call a different isotopic composition to the water on the Earth. Basically, put simply, that means that it's a different kind of water. And so that really casts some doubt as to whether comets, or certainly that kind of comet, could be the major source of the arrival of water on Earth. But certainly we are studying comets more and more. We had our first close-up views of a comet in 1986 when we saw Comet Halley, of course, from a couple of spacecraft, and we've had some great observations. But that Churyumov-Gerasimenko, David, you might remember that. I had a rubber duck on my desk in the planetarium to remind me of the shape of that comet. It was said to look like a rubber duck. Just absolutely amazing. Two pieces joined together. Let's get back onto the chat, and we'll just see if we have some other questions that have come up here. Nothing at the moment, but David, what are your ideas, or Beth, perhaps, about where in the universe? What do you think?
I'm not a fan of panspermia.
Panspermia.
Panspermia. It could be out there, but Martin, I don't know. I just look at our little planet, so I'd have to take your advice on that.
Well, we'd still have to be saying that water's a great place to start, isn't it? I think. Beth, what are your ideas?
I think it's almost certainly out there somewhere. The universe is a big place, and there's a huge diversity of conditions that life lives on here. I'm not a xenozoologist or anything like that, but I had been told by someone that extremophiles on Earth could actually live in the conditions on Europa or Ceres. So if that's possible, then I really do think it's very likely that we'll find life somewhere else. I do mathematical models of food webs, and there's so much different shapes they can be on Earth, from the very deep. I mean, if people can imagine having a lake under the ocean, so super salty water that literally looks like a lake with a shoreline and different animals living in different spots, and all of that is at the bottom of the ocean. So you've got those kind of diversity of life on Earth around the sea populations with enormous bivalves that are the size of lunch boxes, and things that might be a cockroach where we live would be the size of a football down there, right through to the other extreme where most of the viruses on the planet are still in the ocean. And then you've got the blue whale, the largest animal ever. I think diverse life has shown that it's going to take every shape possible. So if there's a little hole for it anywhere in the universe, I think it's going to find it and make life there too.
And Beth and David, could that include life that does not depend on any way on water? Are there any ideas about that?
So in theory, I'd have to say it's a possibility, but I think it's been fairly roundly assumed by most scientists that water has to feature somewhere in life. It's hard to find other liquids that do everything that water does. So it's possible, but I would say it's more than likely that water will be involved in life from my perspective.
David?
Yeah, unless it's predator out of Alien Predator, which has green blood, which, no. I think that's right. Water seems to be one of the essential elements.
Yeah. So this concept that the search for water is equivalent, or so tied in, I should say, with the search for life is quite a reasonable one, and it's why, for example, Mars is so important at the moment, to learn about the water on Mars, the history of water on Mars, when it flowed, where it flowed, and perhaps search for evidence that there was indeed life there. And that's one of the things that spacecraft are trying to do. Going back to 1976, when the Viking probes landed on Mars, they had experiments to try to detect the presence of life, but unfortunately they were inconclusive. But the more craft that go there, the more we'll learn, and as we know, there are some new ones on the way there now, including NASA's Perseverance rover, that will hopefully tell us a lot more about that possibility. We're running out of time now. now, and I don't think we have any more questions either. So thank you very much, everyone from Tasmania, other parts of Australia and around the world for joining us here at the Queen Victoria Museum and Art Gallery this morning. Tomorrow at 10 o'clock, we'll be meeting up again with David because he'll be taking a look at our brand new exhibition here at QV Mag entitled Estuary Below the Surface. I'm really looking forward to that, David. We'll see you tomorrow morning. And I'd like to thank you and also Dr. Fulton. Beth, thank you so much for coming along and speaking with us this morning. And perhaps we'll be able to speak with you again on live streams in the future about this fantastic topic. So I'll say goodbye from me. David?
Thank you for joining us.
And Beth?
Thank you. Thanks for having me.
Bye for now, and thank you, everyone.
Yeah.